So, hello everyone. My name is Aseem Paranjape. I work here at IUCAA. I work on topics related to cosmology and large-scale structure of the universe. And in this series of lectures, I am going to give you a brief overview and introduction to basic cosmology. So, you have presumably already gone through courses on basic ideas of astrophysics surrounding us, and you would have gone on, and you would have taken courses on the structure of stars and basic astronomy, what our local surrounding volume around us looks like, the solar system, our galaxy, etc. So the topic of this particular series, which we will now go through in the next four lectures that I will give, two today and two tomorrow, this works at very different length scales and also in several applications very different time scales. Okay, so we will go over this as we progress through the talks. But before I give any details of what I'm going to talk about, I wanted to give you already a review of the literature, books that you can use in order to get started in this field. So, this is not only a summer school, it is also a refresher course. So, both kinds of participants, I think, will find it useful to have access to these books. You are now, unfortunately, online, you're not visiting here in person, but you can try to get some of these books through online access as well. Okay, so I have listed several books here. All of them are excellent books on one or the other aspect of cosmology. Cosmology, as you will fully appreciate through these lectures, is a very vast topic, and different people focus on different aspects of it. Okay, early universe, late universe, relativistic, non-relativistic, etc., etc. So I have listed several books here. Some of them are introductory material covering a broad range of topics. Others are more technical material covering specific topics in detail. Like I said, all of these are good books, but I have highlighted a few of them in bold, in particular because they have been influential for me. So all of them have been influential to some extent or the other, but these particular books I have found to be extremely useful as a beginner. Okay, so especially for the students in the audience, or even if you are a teacher and you have been away from astronomy, astrophysics for a while, these three books I would recommend very warmly. The first one is by Jayant Narlikar. It is pretty old, it's a bit dated, but it is still extremely good as an introduction to most of what we will cover in this series of lectures. Okay, and it is also very concise and therefore packs in a lot of material as well. The other one, Modern Cosmology by Scott Dordelson, is one of these advanced and targeted books. It is meant to be a book on linear perturbation theory and its applications in cosmology. We will briefly touch upon this towards the end of our course, and you will hear much more about this in Tirthankar Roy Chaudhury's lectures later. And finally, the book by Mo, Vandenbosch, and White. It covers a really wide range of topics, but it focuses on galaxy formation and evolution, as the title suggests. It also covers most of basic cosmology and several advanced topics that are then needed in order to understand the astrophysics of galaxy formation and evolution. Okay, so this is where you can read up on things because, as you will appreciate, also going down the line, I cannot cover all the topics in all detail. Okay, we have only 4 hours to work with. So I will give you a feel for what are the kind of questions that people ask and what are the kind of tools that people use. And then these books and research articles will help you to progress further. Another interesting question that students used to, come up with or get confused with when I was teaching courses in cosmology is what are the prerequisites for starting to work on theoretical cosmology as far as research is concerned. Okay, so again, since this is both summer school and refresher course, I think it makes sense to have an understanding of what you should be good at if you want to start working on theoretical cosmology seriously. Okay, of course, if you just want to get a feel for what people do, these lectures will probably be enough. But if you want to go beyond, then what is required? And this is a biased list because it is biased by the way I think. But for what it's worth, I think that, first of all, of course, you need all of basic physics at the MSc level, because cosmology really touches upon every single aspect of physics that you might have learnt of at undergraduate and postgraduate level in some way or the other. Then a key thing that is required is a working knowledge of basic general relativity, because modern cosmology is built on GR. And you will see in these lectures that knowledge of GR is actually a prerequisite here. I've also listed a few things in italics here. These are okay. If you don't really have them, you can still do research in theoretical cosmology. But if you are good at these things as well, then it will allow you to explore questions which otherwise may not have been accessible. Okay, so one of these things that I've listed along with basic GR is quantum field theory, especially if you want to work on aspects related to the early universe, which deals with the very high energy regime of cosmology. The second thing that is absolutely essential is mathematical methods for physics. This is crucial for doing various calculations, and combined with a knowledge of GR, this gives you a solid mathematical background for pursuing cosmology. The other thing that is needed is a very strong grasp of statistical techniques, because especially if you work on the late time universe, where, as you will see in towards the end of this course as well as in Tirthankar's course, the way we try to describe observations is through very sophisticated statistical techniques. Okay, so sophisticated if you are a BSc student who has not come across many of these things before, but as you start progressing, you realize that many of these techniques are actually very routine in this field. So it is good to have a sound grasp of basic statistics. And again, it is also good if you would know how to use these statistical techniques not only to theoretical calculations, but also how to apply them to data, because the interface between theory and data is something that is very important for cosmology in the current times. Okay. And finally, proficiency with numerical analysis, because this is maybe true for all subjects of astrophysics now, that all the easy calculations have been done 20 years ago. Okay, so if you really want to do something new, you have to be good with computers, because that is where the current state of the art stands. So you have to have some feeling for how coding is done, how simulations are run, etc. And finally, a thing which is desirable, although you can get away without it, but it is quite desirable for theoretical cosmology, is a sound grasp of observational constraints. Without this, you can produce papers, on theoretical calculations, which may have some interest for a small number of people. But if you also understand how observational constraints are placed and what they tell you about theory, or what constraints are placed on theory, this allows you to reach, it allows you to integrate much better with the cosmology community. The theory that you work on becomes more relevant because it can be constrained by observation. Okay, so if you understand how this crosstalk happens, it is a very good thing. Okay, so enough of judgmental lecturing. Let us move on to the actual physics that we would like to discuss. So let's start with something simple, and this has to do with distances in the universe. You've probably come across this already in the introductory lectures. Okay, I see a chat question perhaps, but unless it is okay. So these kind of questions you please ask in the Google sheet, or you can raise your hands later. I will not interrupt myself in the middle of the talk unless it is very crucial. Okay, so let's come to distances in the universe. So this I'm sure you've seen at some point or the other, okay, in some lecture or the other, or in your reading. So let's start with distances that are close to us, which we can maybe hope to imagine. Yeah. So one astronomical unit is the average distance between the Earth and the Sun, and this is already at the level of 100 million kilometers. So it is much larger than humans are used to, but it is at least something that astronomers or even beginning astronomers, amateur astronomers are routinely in touch with. The next interesting distance is the light year, or for most astrophysicists and astronomers, a more relevant way of thinking of light years is the parsec. Okay, so a parsec is something like 3.25 light years. You've come across the definition of a parsec in your previous courses. So this is already going to be something like 100,000 times larger than one astronomical unit. So for example, here is a cartoon taken from Wikipedia, where you can see the sun, the earth, And then this is a logarithmic scale over here, and what is shown is roughly a distance of the order of 5 parsecs, which is something like the distance to the nearest star, Alpha Centauri. Okay, so this is where we are with a few parsecs. Distances between stars are of the orders of few parsecs. The next interesting distance is what happens when there are thousands and or billions of stars in a volume. Okay, so the next interesting distance happens to be of the order of tens of thousands of parsecs. So then it becomes useful to club 1,000 parsecs into a kiloparsec. And for example, here is an artist's illustration of our Milky Way galaxy. And the cutout is supposed to be of the size of 50 kiloparsec or so. Okay, so now we are talking about very, very large collections of stars. These are organized as galaxies. The galaxies themselves have interesting structure like spiral arms, etc., a lot of gas in them. And the typical length scales are of the orders of tens of kiloparsecs. Galaxies themselves can organize themselves into groups and clusters. So, for example, on the right here, you see a picture, I think, of the Coma cluster. And here, individual galaxies can be seen as these blobs, some of them. Okay, and they are almost getting to be like point objects, but you can still see some structure in them. And this cutout now, it's an optical image, is on the order of several thousands of kiloparsecs. So now it makes sense to club those together, 1,000 kiloparsec, to club them together into 1 megaparsec. And this is like 10 megaparsec. Okay, so from a few parsecs, we have reached 10 megaparsecs, and these are the scales of clusters of galaxies. In cosmology, we have to work at even larger length scales than this. So we are going to work with length scales where, at least in the late time universe, individual galaxies cannot even be resolved anymore. They appear like points on a graph. So here is an image which is a real image of our surrounding universe, in which each point that you see here is actually a single galaxy. Okay, and you can see that there are millions of such points here, and these millions of galaxies have been observed, in this case by the 2-degree field galaxy redshift survey. Don't worry about this term redshift, we will come to it in a second. For now, you can just imagine that what has been done here is that a telescope was pointed in the sky, and in the sky, as you know, there are two angles, RA and dec. So one of these angles, the declination angle, has been collapsed, and the RA, our right ascension angle, has been shown here. Okay, so this is a polar plot in which one angle has been shown, the other angle has been collapsed, and this axis here, what is called redshift, which we will discuss a few slides down, you can think of it as a measure of distance away from us. So you are sitting here as the observer on Earth, and you are observing galaxies far away from you. Okay, so the further out you go, the further away these galaxies are in terms of distance. And you can see, as I said, that each of these points is a galaxy. So you have seen these galaxies now out to very large distances compared to their sizes. And you can clearly see that they are not randomly distributed. There is a pattern to them. Okay, so and in some places there are many galaxies, in other places there are not so many galaxies. It is almost like a spider's web. And in fact, the technical term that is now used for this pattern is called the cosmic web since about 30 years ago or so. So here is a zoom in image of a similar galaxy survey. This is from a much later survey. The 2DF Galaxy Redshift survey was in 2001. This one that I'm showing you is a survey called Vipers, which was done in 2013. It's a similar image. But now what you can see also along with this redshift measure, you actually have the distances in megaparsec. And you can see that we are now talking about thousands of megaparsec. Okay, so compared to what we were saying before, we started with parsec scales at the level of solar system, then kiloparsec scales for individual galaxies, megaparsec scales for clusters of galaxies, and now thousands of megaparsec for the spread of the galaxies around us in the whole universe. And here again, just like you can see here, okay, so imagine that this redshift is basically a linear measure of distance. So a redshift of 0.8 corresponds to about 2000 megaparsec. Okay, so if I just switch back, here we only went to redshift of 0.2, which is a factor 4 smaller. So if this was 2000 megaparsec, that would be something like 500 megaparsec. Okay, so 500 megaparsec away from us, the structure of the universe looks like this. Or let's say this is like 300 megaparsec away from us, structure of the universe looks like this. 2000 megaparsec away from us also, the structure of universe looks pretty similar actually. There are places where there are lots of galaxies, places where there are no galaxies. Look at this place. This little blob here where there is nothing is, if you look at the length scale, this is like 30 megaparsec across. And it is not as if the telescope was not able to look at this path. The telescope has looked here, but it has not found anything. Okay, so there is a genuine underdensity of galaxies in this region, complete paucity of galaxies over a length scale of 30 megaparsec or so. Okay, 30 megaparsec, but there is simply no galaxy available. So it's a pretty fascinating structure, and other places where you cannot even tell the points apart, so very, very dense regions. So this is one very interesting fact about our local universe, that when we look out to distances of few thousands of megaparsec, we see this very intricate pattern of a cosmic web of galaxies. Okay, so it's a fact of nature around us. There is another fact of nature which has been observed through a very different kind of measurement. So what we now know is that there is a uniform radiation bath, a bath of photons, which is distributed according to the black body spectrum. And as you know, the black body spectrum is characterized by a single number, which is the temperature of the spectrum. And this bath of photons has a temperature of around 2.7 Kelvin around us. Okay, so what is shown here, it just looks like a green ellipse. But imagine if I asked you to plot the map of the Earth on a flat sheet of paper. I'm sure you have seen something called the Mollweide projection, where you take an ellipse like this and you plot every single point on the spherical surface of the Earth. You can try to map it onto this ellipse. Now imagine doing this to the night sky, okay? And instead of the spherical surface of a ball, you are sitting inside the ball now, and you are mapping the points on the surface of the ball to an ellipse like this. What is represented here is a map of the temperature of this radiation bath around you in the sky. And the reason it looks like a green ellipse is because at this level of resolution, where I don't go beyond 3 decimals in the temperature, this bath actually looks exactly uniform everywhere. Okay, so very fascinating fact about the universe, that there is a bath of radiation with exactly the same temperature everywhere in the sky, up to something like at least up to 3 decimal places, okay, 2.725 Kelvin. In fact, even to higher decimal places. Now, if I start asking questions about at the 4th decimal place, are there variations as a function of angle in the sky? What I find is that indeed there are variations. So now it becomes useful to talk in terms of relative variations. So delta T is the deviation of temperature at any point in the sky from its mean value, which is 2.725 Kelvin. Okay, so I pick a point in the sky, I subtract 2.725, and I call that delta T. And I divide that number by 2.725, the mean value. So this delta T over T is a dimensionless quantity and gives me the relative amount of fluctuation in the temperature. So if I resolve my eyes, if I start becoming sensitive to temperature fluctuations of the order of 10 to the minus 3, I see something like a dipolar pattern in the sky. Okay, and I can interpret this dipole in terms of a velocity dipole, like a Doppler shift of a radiation bath, and the corresponding magnitude of the velocity for a 10 to the minus 3 relative fluctuation turns out to be about 600 kilometers per second. And this is generally attributed to the fact that we are not stationary with respect to this uniform radiation bath. We are moving in a certain direction with a velocity of around 600 kilometers per second. And such a motion will create a Doppler effect. And that Doppler effect is what we are measuring here. Okay, so this cosmic microwave background, microwave because these temperatures of 2.75 Kelvin correspond, the peak frequencies correspond to microwave frequencies. Okay, so this is the cosmic microwave background, which pervades all of the cosmos around us. It has temperature fluctuations of the order of 10 to the minus 3 relative to the mean. Suppose I start becoming sensitive to even finer variations in the temperature, even tinier variations. This was a success. Okay, the experiment I'm showing you is relatively recent. It is from the Planck satellite, but there is an equivalent experiment which was done substantially longer ago in 1993, the Kobe satellite. So the Kobe in 1993 was the first satellite to discover that at the level of 10 to the minus 5 variation, there is a pattern in the temperature around us. Okay, the temperature is not exactly uniform, it is not dipolar. It in fact looks like what is called a Gaussian random field. Okay, so at every location, the temperature is some fluctuation. And if I take the collection of these fluctuating pixels around me and I look at their statistics are extremely well described by a Gaussian random field. Okay, so these tiny anisotropies in the temperature around us at the level of 10 to the minus 5 are believed to be due to primordial physics. Primordial in the sense something happened in the early universe which led to these anisotropies. Okay, and we will see what the current understanding is of these anisotropies. But what I wanted to emphasize in these three slides is that other than the cosmic web, this is an extremely interesting observational fact about our universe, that there is a uniform temperature radiation bath of 2.725 Kelvin with of the order of 10 to the minus 3 Doppler imprints, which could be due to our local motion with respect to the bath. And more interestingly, 10 to the minus 5 variations relative to the mean coming presumably from a primordial origin. Okay, so these are the things that we would like to understand. We want to ask the question, how did all this come to be? What is the connection between the cosmic microwave background that is supposed to be primordial? We will see why it is supposed to be primordial, and the cosmic web that is more local. All right. So the topic of discussion is going to be in the framework of the hot Big Bang cosmological model. Hot Big Bang, this is something that has historically come up in starting from the the early 1920s up to the early 1950s or so. And we will discuss a little bit of the history of this Big Bang cosmology as we go along. But right now, let's just stare at this image, which I stole from the internet. And it gives you on a logarithmic scale the kind of times and energies that are important at different epochs in the universe as per this hot Big Bang cosmology. So we will discuss a little bit about how people develop these ideas. But this slide gives you an overview of the current understanding of this hot Big Bang model of cosmology. So in this model, what one understands is that the early universe was extremely hot and extremely dense. And the earlier you go, the hotter and denser it was in the past. And as time progressed, the universe expanded. And as it expanded, its constituents cooled. Okay, so the temperature went down. And for starting from this hot, dense phase, it became a cool and not dense phase. And then many different physical phenomena happened along the way, some of which we will discuss. And eventually, the constituent components of the universe organized themselves into gas and galaxies and the cosmic web that we see. Okay, so for example, some of the things that happened in the early universe are connected in this picture to very high energy physics, because the universe was extremely dense there and particles were the plasma was sufficiently dense that collisions between particles could occur very rapidly, and energies were so high that even very high energy particles that we struggle to produce in laboratories like CERN were easily produced in the universe at that time. Okay, and so this is around these epochs of 10 to the 15 GeV and cooler, where various kinds of these squarely fall in the realm of high energy physics. Okay, so this is where I was saying that an understanding of things like quantum field theory, etc., is useful, because in these epochs, it's high energy physics which dominates the relevant mechanisms at play. At even earlier times, there should have been epochs in the universe with even higher densities than we are used to, even discussing theoretically, or things that have been like experimentally established in labs like CERN. Okay, so at very early times, you are now in the regime where you have to speculate in some sense about what theories might be relevant here. So there is the epoch of grand unified theories, and even before there might have been an epoch of quantum gravity. These are not observationally accessible at present. They may or may not be observationally accessible in the future. But again, many people like to think about what the universe might have been during these extremely early epochs, where we are talking about a tiny, tiny amount of time, of Planck time, away from the initial point. And this is the key to this hot Big Bang model, that all of our mathematical models seem to imply that there was an initial point of time. And at that initial point of time, all of our models actually break down. Okay, because at least the standard models that we are used to in classical physics. The reason they break down is because at this initial point of time, the densities that we are mathematically talking about become formally infinite. And once you have an infinity in your problem, physically things don't make sense anymore. So at these epochs, what people have been trying to understand is what exactly happens, in the sense, what theory should replace your ideas of general relativity when you go very close to the origin. Okay, so this problem of the origin of the universe is a very long-standing open problem. There are several ideas in string theory, in loop quantum gravity, etc., for how this issue may be addressed. I will not be touching upon any of these in this series of lectures. Okay. Now, at later times, interesting things also happen. So, once the universe becomes cooler than 100 GeV or so, the kind of physics that is important is still high energy physics, but it is well tested in the lab. Okay, so we have had almost a century now of high energy physics experiments in the lab, in accelerators, and we have understood a lot about the standard model of particle physics. So most of the things that we know from the standard model, particle physics, start becoming applicable here, except that things are in a very specific context of an expanding and cooling universe. So these ideas were put together in the 1930s, 1940s, 1950s, and this hot Big Bang model of cosmology was developed, where several very sharp and very precise predictions were made about what kind of elements, nuclear elements and atomic elements, should be produced as the universe progresses through its evolution. And many of these predictions have been vindicated by observation. So, in the next lecture, we will see some of these observational constraints and how they compare with the theoretical predictions. And then, substantially later, the realm of astrophysics took over. When the universe became sufficiently cool that high energy physics is not relevant, but astrophysics is relevant. And eventually, galaxies formed and structure emerged. So, this formation of galaxies and the emergence of the cosmic web, I will only briefly touch upon in the last lecture. Tirthankar Roy Chaudhary will touch upon these things. He will discuss these things in much more detail. So this is again a different way of seeing the same picture. Now the scales have been switched around a little bit, and all of the stuff that I will not discuss has been pushed all the way out here. Okay, and the stuff that we will discuss has been shown here. So these are all freely available on the internet. So I'm not going to spend much time on this. You can go and look at them yourself. Okay, so let's start with a little more detail on what we are going to discuss. So we will talk about relativistic cosmology, which means cosmology in the framework of general relativity. In GR, as you know, the basic picture is that you describe space-time as a curved manifold, and the matter and energy content of this space-time tells the space-time how it should curve through the Einstein equations. So the basic things that you need to work with are to write down a metric for your spacetime and an energy momentum tensor for the energy and momentum content of the matter. And then you combine these two through Einstein's equations to produce solutions. Okay, so this is what you do in GR, and now you're going to do the same thing, except that you want to describe the whole universe at a go. So, if you are talking about the entire universe, it makes sense to not worry about every single atom in the universe and every single planet in the universe, and not even worry about every single galaxy in the universe. You just say that I will close my eyes, or I will squint my eyes, I'll take off my glasses so that everything looks blurred, and think about length scales where more or less the distribution of matter in the universe is smooth. Okay, you can always try to do this. And observationally also, there is enough evidence that it is not a bad approximation to smooth things over hundreds of megaparsec scales and pretend as if once you have applied 100 MPC smoothing, things are basically the same in all locations and in all directions. So in this context, you can write down a formal metric which would be relevant for observers who see a homogeneous and isotropic spatial slice around them. This is called the Friedman-Lemaitre-Robertson-Walker or FLRW spacetime, and its metric looks like this, where this is time, and there are three spatial coordinates written in polar coordinates for convenience. So there's an r coordinate which is radial, and theta and phi are angular coordinates. And you can see that theta and phi have organized themselves into this metric on a sphere because this space-time is isotropic. So there is spherical symmetry if you pick a point as the origin. Okay, and you can pick any point as the origin. That is not a problem. Once you pick an origin, then you can use radial coordinates centered at that origin. The radial direction r appears in this particular way. So if this k, which is supposed to be a constant, if this k were 0, then the quantity in square brackets would look exactly like the metric of three-dimensional Euclidean space. So clearly this k is telling you that space need not be three-dimensional, three-dimensional space need not be Euclidean. So k is telling you something about the non-Euclideanness of 3D space. It is in fact related to the constant curvature of these three-dimensional slices. And finally, we want to discuss evolving cosmology. So the time evolution is entirely captured by a single function, a of t, which is called the scale factor. Okay, so this is the way the metric is organized. And physically, what one is saying is that let's use the fact that there is a cosmic microwave background around us. So consider all the observers who would see a uniform isotropic cosmic microwave background around them. Its temperature may change with time, but in all directions, they see the same temperature. And ask for those observers who see the same temperature as each other as well in all directions around them. Okay, so what are the coordinates which would be used by such observers? These r, theta, phi's are exactly those coordinates. Okay, they are the coordinates which are co-moving with these fundamental observers. The fundamental observers are defined to be those who see a homogeneous and isotropic three-dimensional spatial slice or a homogeneous and isotropic CMB. The corresponding matter and energy momentum content of such a space-time, because of the high level of symmetry in this space-time, this content must have a perfect fluid form. This can be very easily shown. And therefore, its energy momentum tensor turns out to be a very simple form. It is diagonal with only two functions, the energy density and the pressure of the fluid that you are trying to describe. Okay, and again, because of the homogeneity, that is the translational invariance of the space-time, the density and pressure can only depend on time. They cannot depend on space. Otherwise, things would be inhomogeneous. Okay, so this very simple setup is required. And this setup you can plug into Einstein's equation. And then you solve them and see what comes out. So this is what one wants to do. And it is now useful to start working with this kind of setup. And one of the interesting things that comes out very naturally from such a setup, even without solving Einstein's equations, in fact, just from using the FLRW metric, is a connection between a very interesting observable quantity and cosmic time and cosmic distance. Okay, so let's unpack what I said here. First of all, let's recall that we are working in the context of general relativity. GR is based on special relativity, right? In special relativity, one of the fundamental postulates is that the speed of light is a finite constant. And as you know, because of this, time and space become connected to each other. So if I am observing something which has emitted light very long ago, it must mean that that quantity is at a large distance to us, compared to something which emitted light very recently and I'm observing it at the same time. This second object must be closer to us. So time and space are very simply connected using the finite speed of light. What happens with the FLRW space-time is another interesting physical effect, which is that the wavelengths of photons which propagate in this space-time, these wavelengths increase as a function of time if the scale factor of this space-time is an increasing function of time. Okay, basically these wavelengths become proportional to the scale factor. So if the scale factor is increasing as a function of time, as you expect in an expanding universe, then each photon has its wavelength, which will increase proportionally to this scale factor. And now, suppose I have a clump of gas, okay, and it is emitting, let's say, it is emitting an oxygen line, for example. It is at a sufficiently high temperature that it emits an oxygen line. This oxygen line, when the gas clump emitted that line, would have a wavelength which is determined by atomic physics, because we don't think that atomic physics has changed as a function of time in the universe. This is the fundamental assumption we will make. However, once the line has been once these photons have been emitted, they are now subject to propagation on this FLRW space-time, and the wavelength of this line that you're observing, that you will observe later, this wavelength, as time progresses, it increases. Okay, it becomes longer because the universe has expanded. This elongated wavelength you will observe in the lab today. Okay, and you also know atomic physics, so you can predict what the emitted wavelength should have been from atomic physics. So if I now compare the observed wavelength to the emitted wavelength, and I compute the relative difference, which is observed minus emitted divided by emitted, and this relative change in the wavelength, I call it Z. This is it is exactly the same as what you think of as Doppler redshifts and blue shifts. So this is called the redshift parameter Z. This quantity in the FLRW space-time, I can connect theoretically to the scale factor at the value of the scale factor at the time when the photon was emitted. Okay, so the redshift of that you observe for a particular line is related to the value of the scale factor at the time when that line was emitted, which means that this redshift, which you can sit in your telescope room or something and observe, this is directly connected to the time at which a cosmic source emitted light. This is very nice because it is a clock that you can impose on the universe. And because of the finite speed of light, all clocks are also measures of distance, because the longer it took light to reach us, the further away that object must have been. Okay, so this is why this quantity redshift is a useful indicator of distance away from us. And that is what was done, in fact, in the first plot, which I showed you, where redshift was used as a proxy for distance. Okay, so this is a very interesting fact about FLRW spacetimes. Now, beyond FLRW spacetimes, if you now plug in, you use these spacetimes and you plug in Einstein's equations. The Einstein equations, you have gone through a course on this and you have seen that they are very complicated, non-linear, coupled, partial differential equations. But the nice thing is that we are in a very, very symmetric situation. Okay, so these large number of coupled nonlinear equations, they become a very small number of ordinary differential equations. Still nonlinear, but ordinary differential equations, and they are written down here. The only quantity that changes with time is the scale factor, and there are two equations governing its evolution. Okay, one second order equation, one first order nonlinear equation. The first order equation acts as a constraint on the second order equation. Okay, and on the right hand side, you can see the influence of all the energy momentum tensor constituents, the energy density and the pressure of the fluid. And you can also see this constant K appearing, which was related to the spatial curvature of the three-dimensional slices. So let me just quickly go back here. So remember, there was this constant K, which came from the metric. The scale factor is the dynamical variable that we want. And the energy density and pressure came from the right-hand side. So all three quantities appear, and these are the equations you want to solve. And in the energy density and pressure, at least in the standard model, which we will discuss going down, you usually split these components into different parts. One is cold dark matter, one is ordinary baryons, one is radiation, one is dark energy. Each of these we will discuss in detail as we go along. And I have already put down some nomenclature here. So what happens is that this quantity H, which you have defined here, if you notice how the way it is defined, the scale factor usually, I mean, there are different conventions for this. In my conventions, the scale factor is dimensionless. In some other conventions, the scale factor has units of length. But in all conventions, this quantity 1 over a dA by dt is the dimensions of the scale factor cancel out, and it has units of 1 over time. Okay, so this H which is 1 over a dA by dt, is an inverse time. It is called the Hubble parameter after Edwin Hubble, whom I will discuss in a second. And this Hubble parameter, because it has dimensions, it can be combined along with Newton's constant to produce a very interesting dimensionful quantity, which is called the critical density of the universe. So 3h squared divided by 8 pi g has units of a density, and this is called rho crit. So all the densities that you see here, you can divide by rho crit in order to get a dimensionless quantity. So each of these omega i's is defined as the corresponding rho I divided by rho crit. Okay, and also this omega curvature, it is not corresponding to any density as such, but it is related to the spatial curvature of the FLRW space-time, and it is defined like this. So this particular equation, which is named after Alexander Friedman, again I will discuss in a second, this is called the Friedman equation, and it connects together the Hubble parameter, the total energy density of matter in the universe, all components of matter, and the spatial curvature of the universe. Okay, so this quantity is what we are after. And what one can show is that this quantity at late times, the value of this quantity, it is in fact the proportionality constant between a very interesting relation. This relation is between the observed redshift, or the equivalent Doppler velocity, if you like to think in those terms, of the wavelengths of light received from different galaxies versus the distances to these galaxies. So this linear relationship was discovered by Hubble and Lemaitre in the 1920s. And it is one of the cornerstones of modern cosmology. It was the one quantity which convinced people that the universe is expanding. Okay, so there is some human history here, which is very interesting. So these equations, and how did they come about? So the primary person responsible for thinking like this was, of course, Albert Einstein. He had already put down in 1916 to 1919 his general theory of relativity, and he had been applying it to various situations: perihelion precession of Mercury, and gravitational lensing, etc., etc. And one of the things that he applied it to was the universe as a whole. Okay, and I will again come to these very interesting controversies that happened at the time. But two other very important theoreticians of the time were Alexander Friedman and Georg Lemaitre. Both of these people were using Einstein's equations to systems like the FLRW metric, and they had derived. So Friedman had derived these two equations, and both of them had applied these equations in different settings. Hubble was an astronomer, okay, and he was one of the towering figures of observational astronomy at the time. And he made two very important contributions. The first one was in 1924 when he discovered Cepheid variables in distant nebulae. Those nebulae were, it was a debate as to whether these nebulae are in our galaxy or outside. By discovering Cepheids and by measuring the distances to these nebulae, he firmly established that these nebulae are actually galaxies like the Milky Way, and they are at very large distances from us. So he was the first person who conclusively showed that our universe is not just restricted to the Milky Way. So he really expanded our universe in a very literal sense. And then in 1929, he on his own discovered this linear relation. Actually, the data points that he used were confined to this little piece of the plot here. And later on, this relation has been extended to larger distances. And at least in the West, this was seen as a very major advance. And this was called the Hubble relation or the Hubble law. And the proportionality constant was named the Hubble constant. Alongside, in 1927, Georg Lemaitre had also derived the same relation. And this part of the history I will come to later. But basically, this is the time period in which these equations and this relation were derived, and this is what set the stage for modern cosmology. Okay. So let's start working with this metric and these solutions and see what the description is. So the different components of matter that we would like to describe are non-relativistic matter, for which the energy density will behave like 1 over the cube of the scale factor. You can think of this simply as mass conservation, so that density goes as 1 over volume. And if I have a matter-dominated system, I can solve these Einstein equations or the Friedman equations, and I can derive an expression for the scale factor. It will go like t to the power 2/3. Okay, similarly, if I have a universe in which there is only radiation, the energy density of this radiation will scale like 1 over the fourth power of the scale factor. Scale factor, remember, is increasing. Okay, so all these energy densities decrease with time. And the reason there will be four powers is you can think of this as number conservation, which is there just like mass conservation. But then also that all of these photons, their wavelengths are increasing. Okay, so their momenta are decreasing exactly like the scale factor, if the wavelength is proportional to scale factor. So that you have to fold in on top of this, and you get a 1 over 8 to the 4. And in the universe dominated by this, the scale factor will behave like t to the power 1 half. So these are all things that you can derive just from simple mathematics of the Friedman equations. Curvature, as we showed here, behaves like 1 over a squared. Okay, there is a k by a squared term. So you can think of this as an effective energy density. It is not really an energy density. But if I have a universe dominated by negative curvature, the scale factor turns out to be approximately proportional to the time. Okay, so this is another interesting thing. And finally, there is this mysterious component called dark energy, which again I will discuss maybe in the second lecture more. For most of the standard model that we will discuss, this component is consistent with being exactly a constant. Okay, and it is related to the cosmological constant, which in fact Einstein introduced, which we will discuss later. And the energy density, therefore, is a constant. And if you are dominated by this constant, then the scale factor actually exponentially increases with time. Okay. Then curvature can also play interesting roles because, for example, if I have models in which there is no radiation and no dark energy, only non-relativistic matter and curvature, then different cases are possible. For example, when I have a positive curvature or when omega curvature, which has a minus sign, is negative, then the universe will initially expand, but then it will not keep expanding forever. It will turn around and eventually collapse. Okay, so these are very interesting models called closed models, first discussed by Friedman, but also known by Einstein, although he discarded them initially. Okay, then secondly, if I have the opposite sign for curvature, I will have a universe which always expands. And the case where this omega curvature or the value of k is exactly zero is the straddling point in between. And in fact, the equations that one has to solve here are exactly equivalent to what happens if I take a piece of chalk on the surface of the earth and I throw it up in the air. Okay, if I throw it with not enough energy, it will go up, turn around, and come back down. If I throw it with too much energy, it will go into a hyperbolic orbit and never come back. And in between, if I throw it with just enough energy, it will go into a parabolic orbit and just reach infinity with zero velocity. Okay, so the same mathematics actually applies to the expanding universe in this situation as well. So it's very interesting. Okay. So this is as far as the dynamics of the expanding universe is concerned. There is also some very interesting stuff related to the kinematics of light propagation. Because you can ask the question, how should I define distances in cosmology? And the reason this is not a trivial question to answer is because the expansion of the universe means that all your Euclidean notions need to be revised a little bit. You cannot just say that, oh, the time spent by a photon in traveling is n number of years, therefore the distance is n number of light years. Okay, it doesn't work like that because the universe has expanded in the meantime and distances have changed, lengths have changed. So, what to do? So, the simplest way that was identified very early on is to say that let us use observable quantities, physical quantities, and construct definitions of distance that look very similar to Euclidean definitions. Okay, I'll show you a couple of examples in a second. And then just work through the mathematics of these definitions and do photon counting and then figure out what the relevant relations are. So, for example, let's start with this quantity chi. This is like the co-moving distance to a particular source. And the reason you get this complicated combination of CDT by A, okay, not so complicated, is because if I go back to the FLRW metric, remember that light travels on null geodesics, so ds squared is 0. And then if I ignore the angular dependence, you can actually show that the light will maintain constant angle as it travels on the geodesic. So the only things that I have to worry about are dr and dt. dt will go on this side. I'll put back a c if I want to keep dimensions right. And then I'll do the integral. Okay, so the relevant time integral that will be needed is when I take dt here and I divide by a of t. Okay, so that's why this c dt by a of t appears. And then once I have this integral, I can plug it into the appropriate spatial integral and I can calculate a co-moving distance, the value of r to a particular source, which shows me a redshift of z. Okay, so I can do these different change of variables, etc. Like I said, redshift is the same as a clock in the universe. Good. So using this co-moving distance, now what I can do is set up the following calculation. Let me define something called the luminosity distance in the following way. Consider the intrinsic luminosity of a particular source which I know. Okay, suppose I have a source whose intrinsic luminosity I know, in the sense that I know how much energy it is putting out per unit time. If I divide this by the observed flux of light that I get at the Earth, this is an observable quantity. This is supposed to be a theoretically known quantity. This ratio is simply proportional to the square of the Euclidean distance in the standard definition of Euclidean distance, 1 over r squared law. Okay, so if I take this ratio and I take a square root with the 4 pi thrown in, I can simply call this a distance. And to make sure I know what I'm talking about, I call this the luminosity distance. Now the non-trivial part comes where I construct mathematically this kind of setup and I calculate what happens when I set ds squared equal to 0 for the photons that I'm counting in this luminosity and flux calculation. Okay, so I send out photons one by one. I make them all obey ds squared equal to 0. And I say the luminosity tells me how many photons were released and the flux tells me how many photons were received. Okay, and then I do this kind of calculation and I find a very simple formula for this luminosity distance as a function of redshift. It is just 1 plus z times this r source, which is this function here. Very nice, because this r source is a completely theoretical quantity. You give me the cosmological model, okay, the values, how much matter there is, how much radiation there is, how much curvature there is, and I can calculate this quantity for you as a function of redshift. So then this dl of z depends now on z, which is observable, and it depends on observed flux, which is also observable, and it depends on intrinsic luminosity, which is supposed to be theoretically known. Okay, so what I will now do is an exercise where I measure the redshift using a spectrometer. I will measure the flux using a photon counter, a telescope, and I will make a plot of the observed luminosity distance versus the observed redshift. Okay, y-axis will be luminosity distance, x-axis will be redshift. Both are observed quantities now. And I have a theoretical relation between dl of z as well, given my cosmological model. So depending on my favorite cosmological model, I will put different curves and I will see which curve matches the data the best. Okay, so I can now use observations to constrain my cosmological models. This is the basic idea of doing distance-based cosmology. Okay, so using the distance redshift relation in cosmology. A similar distance can be defined. Instead of luminosities, you use sizes of objects. Suppose I have galaxies with fixed sizes. Suppose such a system existed. Then if its physical size is known, I can measure its angular diameter that it subtends on the sky. I call that delta theta. And I simply take the ratio of these and I call this the angular diameter distance. Then, just like I did here, I do a photon counting experiment. I take photons coming from either side of the galaxy. I make them go along ds squared equal to 0. And I ask, how does the angular diameter distance depend on redshift? And now, instead of a 1 plus z in the numerator, I have a 1 plus z in the denominator. Okay, so I'm not showing you details of these calculations. They are very nicely done in Narliker's book, so please go and look there. And these relations you can now start using for doing cosmology. Okay. Another interesting thing is that all these distances, if I take a limit in which this z is much less than 1, they all actually theoretically reduce to Hubbles law. Hubbles law, remember, said that the redshift is linearly related to distance. And in fact, that's what you find here. At small distances, this chi source becomes simply proportional to z. With a constant of proportionality, which is the value of this Hubble parameter at the current time, and that value is called Hubble's constant. And now, actually, one should not call it Hubble's law anymore. The contribution of Georg Lemaitre has been recognized officially by the IAU. So this has been renamed to be the Hubble-Lemaitre law for the last few years. Okay, so this is another interesting thing, that Hubble's law can be theoretically derived in this framework. And in fact, Lemaitre is the first one who had done this. You can also do interesting things. You can say, suppose I am agnostic to the kind of matter content that I want to put in the universe, but I want to see what happens beyond this linear law. I can do a Taylor expansion of this chi source as a function of z, and I can start expanding it in powers of z. And now I will get proportionality constants for higher powers of z, which depend on time derivatives of the scale factor. So they don't directly depend on how much matter you have, how much radiation you have, etc. They depend on time derivatives of the scale factor. So if you assume Einstein's equations, you can relate them further to the matter components of the universe. But the beauty of this kind of expansion is that you don't have to assume Einstein's equations. You only have to assume the FLRW metric. So it's a very powerful way of probing nature, because you're not committing even to Einstein's equations. Okay, so people like to do this as well. It's called cosmography. Okay, so these are the kind of things that the kind of tools one uses. So I have summarized so far for you the dynamics of the smooth expanding universe, the notions of distances in cosmology, and how Hubble's law or Hubble-Lemaitre law emerges, and the idea of cosmography. All of these things can be used observationally to place constraints on models of the universe. These constraints we will discuss in the afternoon lecture today. So the last thing I want to do in about 5 minutes, and then I will stop, is the notion of horizons in cosmology. So this is a theoretical concept, but it is a very interesting theoretical concept because it allows us to appreciate some of the rich nature of the theory itself. Okay, so you have come across horizons in the context of general relativity and black holes. Here we are talking about horizons in the context of cosmology. So horizons in general are basically answers to questions like the ones I have listed here. The first question is, how far can we see? Okay, in fact, it has nothing to do with GR as such. If you stand at the beach and suppose I have, there is people are swimming at the beach, and there is there is a lifeguard, and the lifeguard usually has this little tower, right, which is maybe like 5 to 10 meters tall. Suppose I go up there and I stand, and I have a friend who is standing down at the beach, and both of us ask this question: how far can we see? Okay, you know this, that the person standing on top of the tower will be able to see a little bit further than the person standing at the base of the beach. So the answer to this question is that we can see as far out as the horizon. And there is a certain way of calculating this distance to the horizon if you're standing on the surface of the earth on top of a tower, etc. A similar calculation you can do in the context of cosmology as well. Okay, so because there is a time at which everything is supposed to have begun, right? So there is an origin to the universe in the framework of hot Big Bang cosmology, which means any photon that you see coming to you today, the largest distance that it could have come from is related to the earliest time at which it could have been emitted. And the earliest time theoretically available to you is the time of the Big Bang, okay, time t equal to 0. So I can do the calculation of how far away would an object have to be so that the light that it emits at the time of the Big Bang, suppose it were able to do that, it's not possible, but suppose it were able to, if it were emitting light at the Big Bang, it would take time of the age of the universe to reach me, and how far away would that distance be? This is the theoretical maximum distance to which you can see anything, okay, because nothing existed before that time. So this is called the particle horizon, okay, and it is an integral over the distance that photons will travel from the Big Bang to today. So it is written as this integral, yeah. And by change of variables, you can relate this to an integral over a redshift, and then using the Hubble parameter or Friedmann's equation, you can write down this function for your favorite cosmology. And for a typical standard model of cosmology, the kind we will discuss in the afternoon, this number turns out to be of the order of 10 gigaparsec. Giga is 1,000 times mega. Okay, so it is 10,000 megaparsecs. This is roughly the order of the size of the observable universe around. It's a good number to remember, 10 gigaparsec. Another interesting thing is that for typical kinds of cosmologies that one wants to study, this number is always finite. It doesn't matter whether you have dark energy or radiation or matter or curvature. This number is usually always finite unless something really crazy happens in the early universe. Okay, so for most of standard cosmology, this is a finite number. It is a simple conceptual extension of the fact that in a Euclidean universe, the distance out to which you could see would be given by the light travel time. Sorry, didn't mean to do that. Okay, so this is called the particle horizon. Now, there is another question that you can ask, which is how far can we throw? So, not how far can we see, but how far can we throw? Suppose I take, I take a gun and I shoot it. How far can the bullet go? In principle. So, in principle, the furthest that I could manage would be if I could shoot a bullet where the bullet travels at the speed of light. Okay, so instead of thinking about guns, let's think about light signals. How far can I send a light signal? And okay, you may argue that the light signal will become weak because of 1/r² or distance redshift, etc. Let's say we have a powerful enough torch that we can send. There are enough photons that can reach as far as we would like them to reach. So, in principle, how far can we throw signals? The answer to this question is the event horizon. This is the same question you would ask sitting inside r equals 2m of a black hole, of a Schwarzschild black hole. Okay, how far can I throw? And the answer would be you cannot throw beyond r equals 2m. Similar question you would like to ask here, but because you have phrased the question in this particular way, the answer turns out to be easy to calculate. And it is simply the integral of the co-moving distance where you start at time t equal to 0 and you allow the time to reach infinity. Okay, and you are assuming here that the scale factor is well defined far out into the future. There may be space times where the scale factor is not defined at infinitely large times. For example, a universe which contracts and closes up on itself in finite time, then this infinity would have to be replaced with something finite. But in general, this is from T naught, which is current epoch, to the maximum time that is available in this cosmology. And how far is this distance? This distance, again, you can rewrite it in terms of the scale factor now, assuming that the scale factor is a monotonic function of time. And this distance need not always be finite. Okay, so in normal space times where I have only radiation and matter, for example, this distance will actually be infinite. And that kind of makes sense. It is very similar to our Euclidean notion, where if I flash a powerful enough torch, the light will keep going. There's nothing to stop it. But in universes which have a positive cosmological constant, it turns out that this distance turns out to be finite. Okay, so there is an event horizon. So it is as if you are living inside a black hole. It is not really a black hole, it is related more to the de Sitter universe. And you are sitting inside this event horizon and you cannot send signals out. And finally, there is a last length scale in the problem, which is called the Hubble radius, which is it is more of a dimensional calculation where you take the inverse Hubble parameter, which has units of time, and you multiply it with the speed of light, which is length per time. So this c by h is a quantity of dimensions of length. This is not a horizon on its own, in the sense that it is not a distance out to which you can throw light signals or something. Photons will travel. If I send a photon from my location, it will happily travel beyond the Hubble radius around me. But it is an interesting length scale because, firstly, it's an interesting time scale. This H inverse gives you the current doubling time of the universe. But it's also an interesting length scale because it turns out that in perturbation theory, when you want to study growth of structure, this is the length scale which controls which wavelength fluctuations will grow their amplitude and which wavelength fluctuations cannot grow their amplitude. So there is a different kind of causality argument that appears there. It is at the level of growth of fluctuations, and this particular length scale, which is called the Hubble radius, enters there. Okay, so we will come back to this idea down the line again. So this is all that I had to say for this lecture. I am happy to take questions for a little while, and otherwise, of course, we will again meet in the afternoon session. So let me try to navigate. I will just stop sharing screen for a second, otherwise I cannot see anything. So where is that Google Sheet? Okay, so I don't see any questions in the Google Sheet. Are there any questions from the audience? So let's see what was in the chat. Okay. So what comprises observational cosmology? Well, observational cosmology is the collection of things that you would do where you say, I will take data from telescopes or data from experiments like cosmic microwave background experiments, and I will interpret them in the framework of these theoretical concepts that I'm talking about. Okay, so for example, if I take a collection of galaxies around me and I calculate their mean numbers in different places as a function of their mass, for example, and I try to relate this distribution of these galaxies, or I try to relate how many galaxies there are in the overdense regions versus how many are in the underdense regions. And I try to relate this to cosmological questions like how much is the matter density of the universe, what was the level of the temperature anisotropies in the past, etc. Okay, so these are the kind of questions that you would do from an observational cosmology perspective. Okay, so whereas theoretical cosmology, you could in principle say, I don't care about observations. I have the FLRW metric, or I have some other interesting theoretical setup. I will make some theoretical assumptions. I will do some pen and paper calculations, or I will run a computer simulation. I will produce some results. And these are theoretical results. They need not be connected to observation. Of course, this will be a limited exercise. Okay, then let me just go on. I will also come to the people who are raising hands, don't worry. So I will just do an alternating thing. Is the redshift survey done in a plane since declination is no. Redshift survey is done in 3 dimensions. So imagine I have the sphere of the sky, right? And there is distance away from me. So it's a 3 dimensional volume. I can locate where every object is on the sky. So that is 2 dimensions. And I can measure the redshift if I have a spectrum, okay, of lines that I can identify. So that redshift through Hubble law gives me a measure of distance. So I actually have a 3 dimensional location of the galaxy in space. What is shown in that plot, because I don't know how to render 3D. Nowadays, people render 3D also. Okay, so if you go online, you will find examples of this. What I've chosen to show you some of the older pictures where one of the angular directions has been suppressed. That's all. Okay, you just take a slice and you just combine everything into one slice. It doesn't mean that everything was done enough. These are all 3D things. Okay. Let me. Who has raised your hand? Why can I not see you? Oh, here you. Okay, so there is Dwij Brahmbhat. Please ask your question. Unmute and ask.
Hello, sir. Thank you for the talk.
Yes.
So my question is that you basically said we took the lower decimal anisotropies. So for the cosmic microwave background, but why did we care about the like lower decimal anisotropies? Shouldn't we just ignore them?
You could choose to ignore them, but then you would miss out on a Nobel Prize. Okay. So one of the Nobel Prizes of the CMB was given for the 10 to the minus 5 fluctuations. The reason a Nobel Prize was given for it is because it is an extremely fundamental observation to our understanding of cosmology. There is a prediction that you have to ask the question, where did these galaxies that you see around you come from? Okay, and the hot Big Bang model of cosmology says that there must have been tiny fluctuations in the matter density at early times, which then grow under gravitational collapse to become structures today. So, if you do not see these tiny fluctuations, then there is something seriously wrong with your cosmological model. And the fact that we saw these fluctuations was a resounding success of the cosmological model. Okay, so it is an extremely important observation. Does that answer the question?
Thank you, sir. Yes.
Okay. So let me just come to the chat again. Can you please unraise your hand also, the person who had raised? Okay, thank you. So, how is CMB detected? There are dedicated experiments. So basically, it is in some sense a very simple experiment. It's a radio antenna. Okay, and the radio antenna, in fact, that is how it was discovered in the first place. In 1965, there were theoretical predictions that the CMB should exist. Two radio astronomers, Penzias and Wilson, they were calibrating a radio antenna for some other purposes. Okay, and they wanted a very high sensitivity radio antenna. And being very careful, they tried to account for every single source of noise that they could think of, but they were left with this constant background of noise which they could not account for. They went to the extent of cleaning pigeon droppings from their radio antennas, thinking that maybe that is what is causing interference. Okay, but none of this worked. And at some point, they were told by a theorist that there are these other theorists who have been working down the down the road, and those guys have been talking about this theoretical expectation, and they are trying to build an experiment, and they will be trying to detect this in the coming weeks or something. Okay, and that is when Penzias and Wilson realized that what they had is extremely important. So they started talking to these theorists, which included Peebles and Wilkinson, etc. And that is how the CMB was discovered. So it is a radio experiment. This is at the level of the smooth background. If you want to detect the tiny fluctuations, you cannot do it with just one antenna. Typically, what is done is a differential experiment. You take two antennae and you calculate the difference of the effective temperature that you get from the two of them. Okay, so that makes your measurement very, very sensitive. So I would suggest talking to some of the radio astronomers here at NCRA, or even like somebody like Neeraj or Desh, or someone who has been taking your radio physics courses. They will be able to give you a better feel for some of how these experiments are done. Okay. Please explain concept of co-moving distance, like its importance. So concept of co-moving distance, well, co-moving distance is just the distance in for these co-moving observers, in the sense that there is a fixed distance between us and a source. Where, and so, okay. So the scale factor, what is it doing? It is telling you that suppose I had a source which was 10 megaparsec away from me today. 10,000 years from now, how far away will this source be from me? Okay, so the scale factor will increase, therefore the actual distance to the source will change. But what you can do is assign a mathematical distance between these two locations, which is just a label assigned to those points. Okay, so I just need to know that this point is there, this point is here. So I can construct a coordinate system, let's say relative to today. So I will say that today, if I had somehow put down a ruler of 10 megaparsec, that ruler would extend exactly from me up to that point. Then I declare that the distance between me and that point is 10 megaparsec. Okay, and some other ruler would have been 20 megaparsec to some other point today. Then I call that 20 megaparsec co-moving distance. So now tomorrow, the distance between these 2 points may be different and will be determined by the scale factor. In the past, it would also be determined by the scale factor, but this is the co-moving distance. I hope that is clear. I'll take one more from chat and then come to the raised hands. State in cosmology that the universe is 13.8 billion years old, but since time is relative, then according to which clock we are stating this age. So this 13.8 billion years old is in the clock that I showed you in those equations. That is called cosmic time. It is supposed to be the theoretical time which would be used in sync by a set of fundamental observers, all of whom measure the same CMB temperature as each other at any given fixed time. Okay. So basically, all these observers at a given time, they see the same CMB temperature as each other. Let's say 50 degree Kelvin. Then at a later time, all of them will see a temperature which is, let's say, 40 degree Kelvin. So then all of them will say that the time that has changed from the previous point to the current point is a delta T corresponding to the time which it took to go from 50 Kelvin to 40 Kelvin. So they all have synchronized clocks, and that is the T which is used in order to produce this number of 13.8 billion years. That answers the question. Okay, let me do one more from the raised hands. 1 second, please. Why are these raised hands not? Okay, here. There is Pushti. Sorry, the hand disappeared. Okay, I presume you don't want to ask your question again. All right. How exactly the universe is expanding? Can we say anything about density? The universe is expanding. This is an observational aspect. So how exactly it is expanding, how fast it is expanding, can be measured by the Hubble parameter at any given time. Our theory will tell us how the Hubble parameter changed as a function of time. So at different epochs, the universe is expanding at different rates. One of the interesting observational constants is the Hubble constant, which tells us how quickly it is expanding today. What is the current doubling time of the universe? Okay, and densities typically in the standard model will decrease as a function of time, except the cosmological constant, which maintains constant density. Okay, Pushti has raised her hand. I assume it is a lady. Please ask your question.
Yes, sir.
Yeah.
Sir, I have a question regarding low redshift image. So, as we can say that the cosmic web of galaxy would be vanished by the expansion of universe, the pattern of the cosmic web?
Okay, you're asking whether it would vanish because of expansion.
Yes, sir.
Okay, that's a very interesting question. And the answer, it actually depends on the kind of cosmological model that one is working with. Okay, so in a universe where you have only radiation and matter, what will happen is that this cosmic web will kind of remain. And the reason the cosmic web forms, you have to understand, is because gravity is attractive. Okay, the universe is expanding, so the universe is trying to pull everything away from each other, but gravity is attractive, Newtonian gravity. Okay, so gravity wants to bring things close to each other. So once you have sufficiently overdense regions that occur in a particular place, they can become more and more dense, and that is eventually how the cosmic web emerges. So in a universe in which the expansion of the universe is driven by things like radiation and matter, this expansion will tend to always decelerate. Let me quickly share my slide again. So let's go back to the equations. Okay, so you see this acceleration equation. There is a negative sign here. Okay, so there's a rho and a p, and there's a negative sign. For matter, non-relativistic matter, p will be approximately 0. For radiation, p will be 1/3 of rho, but it will be positive, that is. So rho plus 3p will always be positive for matter and radiation, and therefore this negative sign will mean that the expansion of the universe is decelerating as a function of time. In such universes, the cosmic web will form, and in fact, it will keep growing, more and more complex. And eventually, things may happen like a lot of matter may collect together, and black holes may form, etc. Okay, so matter will continue to condense. In a universe which is dominated late times by a cosmological constant or by dark energy, this P will actually be negative, it will be minus rho approximately. So rho plus 3p will be a negative number. Okay, and then combined with this negative sign, this A double dot will become positive. And in fact, this is one of the key aspects of observational cosmology today. We believe that the current universe has entered this phase already. In such a universe where the cosmological constant becomes more and more dominant as a function of time, the event horizon of the universe will start playing a role. So eventually, what will happen is that you will not receive light from the galaxies that are residing in the cosmic web. So then it becomes a question as to what you mean by the cosmic web. So observationally, like in a absolute sense, maybe the cosmic web is still there. Okay, to some super observer, not limited by speed of light constraints, etc. But as far as we know, such observers don't exist. So for any reasonable observer living within the framework of normal physics, we will stop seeing the effects of the cosmic web around us. And in fact, in such a universe, eventually we will become an isolated system. Okay, our Milky Way will become the only galaxy that we can see around us. So it's a very interesting situation, actually. Okay, I hope that answers the question. Let me take a couple more from the chat. Is uniform radiation path considered as ideal at an observational scale of CMB? I am not sure what you mean by ideal. You mean as an ideal, you mean in the sense of the standard thermodynamics of like the statistical mechanics of relativistic plasmas? Then the answer is yes, it is considered like that. Does the dipole image of the CMB appear different if taken from another galaxy a few billion light years apart? It should, yes, because it would depend on the motion from that particular sector. But unfortunately, we do not have access directly to such observations. There is an interesting thing here. There is something called the kinetic Sunyaev-Zel'dovich effect, which effectively uses an idea which is similar. It uses the fact that different galaxies will see a different CMB due to their physical motion. Okay, so you can try to look up this aspect. I don't see any questions, hands raised. Will you be talking about cyclic universe and brain theory? Not cyclic universe and brain theory as such, but I will be talking about some alternative cosmological models at some point. Okay, so I don't see any other questions. We are well over time, so I would suggest let's close this session and meet at 2:30 after lunch. Thank you very much.